First topic this week that we're going to look at is the substitution method. So this is just one of the techniques of integration that we'll study, and it is relatively straightforward. So let's just go through these guided notes, and there are several examples in here. So it says, which of the following integrals would be a good candidate for the substitution method? If it is a good candidate, give the best u substitution. So a good candidate for u substitution would be something where you have two functions, and if you take the derivative of one, that derivative will equal another part of the function. So let's look at A, and I will show you exactly what this looks like. So in A, I have sine of x to the fifth. So if I take the derivative of x to the fifth, I will get 5x to the fourth. So this would be a good candidate. This would be the good candidate with u equal to x, or yeah, u equaling x to the fifth. So that's a good one. For B, the integral of sine x to the fifth power times cosine x. Is there something in here where we would take the derivative and then that derivative would be equal? Well, if I rewrite this function, because this is something that often helps, because you'll see a lot of these are chain rule type functions. Okay, so sine raised to the fifth power is rewritten like that. Then if I chose u equaling sine x, well, the derivative of that would be cosine x. So this would also be a good candidate. So both of these are kind of like classic examples. So let's look at C, integral of x to the fifth times sine of x dx. Well, if I say that u is x, well, the derivative of x is 1, so that's not really going to help me. If I say the derivative or the u value is x to the fifth, then its derivative, 5x to the fourth, is nowhere in that problem. Same thing with sine. There's no cosine, so this would not be a good candidate for u substitution. We have to use different methods for that one. And so part of the problem is just recognizing which, what is the u substitution. So let's look at this problem here. Calculate the derivative of 2 times the square root of 2x squared plus 3. So we're just taking a derivative of this. So if I'm going to rewrite that. So it's y equals 2 root 2x squared plus 3. Well, this is a chain rule problem the way it's set up. So if I rewrite it as 2 times 2x squared plus 3 to the 1/2, you can see that it's a chain rule problem. So y prime would be the derivative of the outer function, so it would be 2 times 1/2, which would just be 1, leaving the inside of the function alone, and multiplying by the derivative of the interior function, which would be 4x. Okay, so that would be the derivative of that. Now you can see that u, or the interior function, was left alone, so 2x squared plus 3. So this is a chain rule problem that is the type of thing that you're looking for when you take derivatives. So, or when you're finding your u substitution. So let's look at this one. The integral sign didn't show up. So let's put that there. So the integral of 4x divided by root 2x squared plus 3. Well, this relates to the previous problem. Okay, so for this one, usually u is going to be something that's inside of another function. Again, it's like it looks like a chain rule problem almost. So u, in this case, I would choose 2x squared plus 3. And the way that I set these up, it's consistent every time. So the derivative of that would be 4x dx. And what we're trying to do, so we're writing this a little different. Notice I have du, and then I put the dx when I take the derivative. What you're going to do is solve for dx. So we'd have du over 4x equals dx. And then we're going to substitute in the problem du divided by 4x for dx. So this first one this will seem like a slow process, and then eventually you skip a lot of these steps. So I'm saying that 4x divided by the square root of u, because I substituted that, and I'm replacing this dx with du over 4x. So here's in blue is the new integral, and I start messing with that a little bit. Cancel out 4x's, and now it's just 1 over root u du. And we have the integral of u to the negative 1/2 du. So this is an integral that I can actually find now. And so I integrate. So I add 1 to the exponent to get u to the 1/2, and I divide by 1/2. So this would be 2u to the 1/2 plus c. And then we substitute back in the u. So 2 times 2x squared plus 3 to the 1/2 plus c. So this would be an example of a u substitution problem. In our next problem, the definite integral from 0 to 2 of 2x squared times x cubed plus 1 dx is solved using the substitution u equals x cubed plus 1. What should the upper and lower limits of the new integral be? So this is a problem, and you can do this wherever it's somewhere that would make the problem easier. We can change the limits and keep it in u. So it already told us the substitution, and I'm going to rewrite this. I just like to work off my own handwriting. Okay, and it already told us that u was x cubed plus 1. So I'm going to go through this. Du is 3x squared plus 1, and then, not plus 1, just 3x squared dx. And then du divided by 3x squared equals dx. Okay, now I'm going to substitute that in. So I'm going to leave the upper and lower limits off for now. And so I would have 2x squared times u times du divided by 3x squared. And we can cancel our x squareds and be left with the 2 times the integral of u du. So this integral is so much easier than the original problem. It doesn't even seem like it would give us this original problem. So now I can integrate this. And what I'm going to say here is these limits now, so if I want to keep this in u and not use x again, I can just take these limits of 0 and 2, plug them in for x cubed plus 1, and get new limits. So if I plug in a 0 for my lower limit, it would be 0 cubed plus 1. So my lower limit would just be 1. If I plug in, put an equals sign there, it says u equals. If I put u equals and I plug in my 2, that would be 2 cubed plus 1, which is 9. So the upper limit is 9. So now I don't even have to resubstitute in x cubed plus 1. So I just integrate this. So I'd have u, or 2 times u squared divided by 2, evaluated from 1 to 9. And the 2's cancel, so that's even easier. And so you'd have 9 squared minus 1 squared. So 81 minus 1 is 80. So you can change the upper and lower limits by just plugging in your x values, your limits of integration, into u and getting new limits. Okay, so let's do this one like that too. Okay, so integral from -1 to 2 of 2 times the square root of 5x plus 6. So u, I'm going to choose it to be 5x plus 6. Take the derivative. Solve for dx. and substitute in. So I would have the integral, and I'll do this slowly. So this is 2 times square root of u, and I'll say that's 1/2. And then dx is replaced with du over 5. Rewrite that. So I have the integral of, or 2/5, the integral of u to the 1/2 du. And again, if I want to just keep this in u, I take my 1 and plug it in right there for x. So u would be 5 times -1 plus 6, or 1. And then take the 2 and do the same thing, plug it in. So u equals 5 times 2 plus 6 for 16. So this limit, the new limits of integration are, the lower limit is 1 and the upper limit is 16. Now I can evaluate this limit. So this would be 2/5 times u to the 3/2 divided by 3/2, which would be times 2/3, evaluated from 1 to 16. And then I clean that up, so that'd be 4 over 15 u to the 3/2 evaluated from 1 to 16. Okay, so now I evaluate that, and we plug in 16. Since 4/15 is a factor, I don't want to have to multiply it twice. So this would be 16 to the 3/2. So the denominator of that would go on the outside. So this would be the square root of the cubic root of, square root of 16 cubed minus 1 to the 3/2. So 1 to the 3/2 is just 1. Okay, so now you're just going to end up with 4/5 times 16 times the square root of 16 minus 1. Okay, so now we have a trig function. So remember, we're looking for something that when we take the derivative of it, it will equal another part of the function. So tangent, in this case, if I take the derivative of tangent, I get secant squared. So I'm going to choose tangent. And you'll know these don't work pretty quickly because you'll make a substitution. It won't work out how you wanted it to, and then you'll have to find some other one. So you can't accidentally do it because it just won't work. So let's say u is tangent. Du is secant squared theta d theta, and then du over secant squared theta equals d theta. So let's make the substitution. So u is tangent, so I will say this is now the integral of u to the 4th, and then times secant squared theta d theta, and I'll really show this one as, we're plugging this in. Actually, no, let's replace d theta with that. So d theta is du over secant squared theta. And just be aware, if you have mixed variables, so right now I have u's and thetas, they should all clear out to just have u. And if it doesn't clear out to just have u in your integral, then you chose the wrong substitution most likely. So these cancel, and now I'm left with the integral u to the 4th du. So u substitution takes these integrals that are more complicated and it simplifies them. And so from this we get u to the 4th, u to the 5th over 5 plus c, since it's an indefinite integral, and then we make our substitution back. So tangent of tangent to the 5th power of theta, and that's over 5 plus c. Okay, so let's do another one more. So this is one where it'd be easy to make the wrong substitution. So initially, when I looked at this, I wanted to just say u is 2x, and then I kind of worked through that. It doesn't work. So you want to say u in this case is 1 plus e to the 2x. And there is some trial and error when you first begin these, because you're going to try to figure out these derivatives. So the derivative of that would be, the derivative of 1 is 0. The derivative of e to the 2x is chain rule. And then you have your dx. Solve for dx. And replace. So this is what we'd have here. It's going to be the integral of e to the x, and I already chose this to be u, and then I'm replacing dx with du over 2e to the 2x. Okay. And so you can cancel these. So we can cancel one of the e to the x's. And I can cancel one of these, which just leaves me with e to the x. Let me rewrite that because that's a little confusing to look at. So this would be du over u, and then you're going to have this 1/2. So that 2 in front comes out. And that's our integral to evaluate. So integrate that. The antiderivative of 1 over u is the natural log of u. So this would be 1/2 of the natural log of u plus c. And that equals 1/2 the natural log of u, and u is 1 plus e to the 2x plus c.